Hello everybody, this is the second video for chapter 4 of the statistical learning class. So in the first video for the chapter, we've introduced generalized linear models, which are a class of models allowing to generalize linear regressions to nonlinear relationships. So in the previous video, we've established the assumptions of GLM models, which were basically independent response variables given the predictors, um, a relationship between the expectation of the response and the predictive variables characterized by the inverse of some function g called the link function applied to the linear combination of predictors. And the last one was that all observations were obtained from the family of exponential or the exponential family of distributions. So we've then discussed how to estimate the various parameters of GLM, a linear generalized linear model, and we finally discussed some statistical tests that could be used to assess the uncertainty around the parameters and to test if some of them are significantly different from zero. So here we'll start the class by discussing other ways to assess the goodness of fit of a GLM model. Because whenever we use a given model for prediction and we estimate the model, it's always good to come up with tests to see if the model matches well the data or if it performs poorly. Because if it doesn't match well the data, then you might prefer considering some other model. So diagnostics or goodness of fit tests is a very useful topic when we apply a statistical modeling technique. So what we're going to discuss here is diagnostics of a GLM based on the so-called residuals. So the first thing we will discuss is visual inspection here. Okay, so in a traditional regression analysis, visual inspection diagnostics are often done by looking at the residuals. So residuals are the prediction errors, and typically if the model is good and well estimated, then the residuals should approximate the noise component epsilon, and therefore residuals should be approximately IID, and if you assume normality, so IID Gaussian with a fixed variance. So to assess if it's really the case, what's often done is to look at residuals. So you can look at residual time series to see if there are patterns that are discernible. You can look at plots of residuals versus explanatory variables to see if there are other relationships that can be observed. So here in the GLM diagnostics, we can still try to use visual inspection, but now what remains to be done is to define what residuals are. Okay, so for linear regression, this was pretty clear, but for GLMs, it's a bit less clear what residuals are because there are multiple ways of defining them. So again, we won't go through all of the possible methodologies to define residuals for a GLM. We'll only present one which can be used. Of course, it's not the only one, but here, if you want to know about all the possibilities, again, you have to go through a formal class dedicated to GLMs only. But now we'll present one such method which can nevertheless be useful. So in this chapter, we will use what we call the Rosenblatt transform to obtain residuals that are approximately IID uniform 0, 1, and then we can apply some tests to see if IID uniform 0, 1 is a reasonable assumption for such residuals. So if it is, then it means the model performs well. If it isn't, then the model does not perform well. So using the Rosenblatt transform relies on the following result of probability. So if y is a continuous variable, random variable, and fy is its CDF, its cumulative distribution function. Then we have that u defined as the CDF of variable y applied onto the variable y is uniform 0, 1. So this result will give the proof. It's not very complicated. So, well, at least I wrote proof, but it's a sketch of a proof, okay? Because we'll cover the case where the CDF is invertible. Okay, if it's not invertible, we need to consider what we call generalized inverses, so the proofs might be a bit slightly more complicated, but to do simple, we'll assume that the CDF is invertible. So let u being between 0 and 1, and let's say f inverse of y is the inverse function of the CDF of y. Okay, so f minus 1 is the inverse of fy. So u, which was defined as fy applied to y, we want to determine what's the probability that this random variable is smaller or equal to some constant u. So by definition, u was fy applied to y. And then because the inverse should be increasing, so f is increasing, thus the inverse should also be increasing. So we can apply f inverse on both sides. And then here f inverse applied to f, it's simply the identity function. So this becomes the probability that y is smaller or equal to the inverse CDF applying u. And this probability is simply the CDF evaluated of y evaluated on this quantity. So this is fy of f inverse of u, which is simply equal to u. Okay, so we have the probability capital U is smaller or equal to that constant small u is small u, and thus u is uniform 0, 1. Now about f being invertible, so because we assume y is continuous, then there's no atom in the distribution, but it doesn't necessarily mean that the support is continuous, so you might have a zero density on a region or something like that. So in these cases where the inverse might not exist, the proof could be slightly more complicated, but the result is the same. Okay, so let's go back here and recall the result. To get a uniform 0, 1, you simply need to apply the CDF to a random variable. So we'd like to do that, and what we would like to do is to take all responses from our data set and apply their conditional CDF given the explanatory variables onto this. Okay, so it can be shown, so these are conditional CDFs, but instead of unconditional ones, but it can be shown that these random variables, the UIs, they would be IID uniform 0, 1 variables. Okay, so this is the result from the Rosenblatt paper, which here, well, in Rosenblatt there's no GLM, but it applies for all vectors of random variables. If we do that, if we define the UIs, okay, the result in the paper is a bit stated differently, but the idea is if you apply jointly the CDFs to each random variables, then you obtain a set of IID uniform 0, 1 variables. Okay. So what we'd like to do is we'd like to apply this transform on each of the responses and determine if what we obtain is a set of IID random variables. So this is what we'd like to do. But here the problem is that beta and phi, in practice, of course, they're unknown. Okay, so we don't have them, so it's impossible to apply this transform on their responses. So instead, what we will do is we will use our estimates of beta and phi and plug them into this to obtain an estimated CDF for each of the responses. And then by using this estimated CDF instead of the true CDF, we'll calculate this transform, and we obtain U hats, which are not exactly IID uniform 0, 1, but approximately IID 0, 1, under the assumption that beta hat and phi hat are well estimated and close to their true values. So the idea is we'll define pseudo-uniform residuals as according to the following formula. So the ith pseudo-uniform residual is obtained by applying the conditional CDF of the ith response with respect to the ith predictors evaluated in the ith response and their data, given your ith predictors in the data, and where you use estimated parameters instead of the true ones because the latter are unknown in practice. So if you have enough data and the data are indeed generated by your GLM model, then you should have that these U hat i's should be drawn randomly from IID uniform 0-1 variables. So if you want to assess if the GLM provides a good fit to your data, you could test if these indeed come from IID uniform 0-1s. Okay, so if they're truly IID 0-1, then you could try to inspect visually the residuals and try to identify trends. Okay, because if you see trends happening, this would violate the assumption that your residuals are IID. So clearly, this would mean there's an issue with your model. Okay, so if you observe trends when you visually inspect residuals, you would have that the GLM is not a good model. Okay, so what we mean by trends, you can have first try to plot the residuals against the various predictors, and if you have a trend, so let's draw a picture here. Let's say you have, okay, so this is I, okay, this is xi, for example, j for some predictor j, and this is ui hat. So if you have a trend, for example, you have observation like this, clearly the residuals are not independent from x. So this shows your IID assumption where, okay, I said IID, but not only are they independent from each other, the residuals should be independent from the predictors also. So if you have something like that, then clearly the GLM model is not fit. Conversely, you could try to look at the time evolution of residuals. So if you have something like this, so for example, this is I, this is ui hat. So if you have, for example, a pattern like this, okay, so this means that clearly there's some form of autocorrelation. The value of I for a given I is clearly correlated to the value of ui minus 1. So here the next value of u strongly depends on the previous one. So if you have something like that, then this is clearly a trend also, and this violates the assumption, the result that the u's are IID. Okay, so trends like this, they would entail that the GLM model is not suitable to represent your data. Okay, so you can look for trends within residuals, which would reject your model, but another possibility is to apply distribution statistical tests to assess if the distribution of the u's is indeed uniform 0-1. Okay, so distribution tests, they include, for example, the Kolmogorov-Smirnov, Kramer-von Mises, or some other tests which are used to test if your observations come from a given specific distribution. Now, once again, I don't want to delve into the details for these tests. Please refer to Wikipedia if you want to have more information, or to like statistical textbooks. I don't want necessarily to expand much more on this. Now, one thing to consider here when you apply these tests is that the residuals obtained from the Rosenblatt transform, they're not exactly uniform 0-1, but they're only approximately uniform 0-1. Okay, so if you compute p-values and the assuming that your null assumption is exactly uniform 0-1 variables, your p-value might not fully be accurate. So there are recent developments in statistics which involve tests allowing to consider the fact of that the uniform 0, 1 is approximately IID. The residuals are approximately IID 0, 1 and not exactly IID uniform 0, 1. But these tests are much more involved computationally. Examples of methods which can do that include parametric bootstrapping tests, but again, these are excluded from the course of the scope of the current course. But I still nevertheless wanted to let you know, in case you're interested by these, you can have a look at these more advanced material. Okay, so we won't study these, but just for you to know they exist. So if you need to apply GLMs in your work or research or whatever, you can use these methods. Okay, good. So once we fitted the GLM, and let's say we've applied statistical tests and the tests indicate that the GLM model is suitable for your data, the objective, as we said, is to now make a prediction for new observations. So let's say we have a new observations and we know there its predictors x0. We'd like to form a prediction for y0. So as we've discussed in the previous video, for that new observation, its point prediction, which is its conditional expectation, would be given by the inverse of the link function applied to the linear combination of the predictors. Okay, this was a result from the GLM, so we had g of expectation of yi given xi was equal to beta 0 plus the sum, beta j, sorry for this, this x I j. Okay, so if we apply g inverse on both sides, we have that the expectation of y, which is the best forecast we can do for y, is a linear combination of these predictors. Okay, so this is a point forecast, but sometimes you want not only a point forecast, but rather a prediction interval. So if you want a prediction interval, you'd like to find an interval of values in which the probability that your observation falls is, let's say, 95% or 99% or something like that. So then, if you want to form a prediction interval of confidence level alpha, and here I've used a bilateral interval, so you might have unilateral intervals also, but often it's a bilateral interval you want. So this bilateral interval would be computed as follows. So you would consider the estimated CDF of your new response, where the estimated CDF given your predictors is the one provided by plugging your estimates of the parameters into the CDF of the observation, and then you'd use the quantiles of level 1 minus alpha divided by 2 or 1 minus 1 alpha divided by 2. Okay, so for example, if alpha is 5%, then the lower end of the prediction interval would be the quantile of level 2.5% of based on your estimated CDF of that observation, whereas here at the top end of the prediction interval would be the quantile of level 97.5% based on that estimated CDF of the observation. Okay, so with GLMs, you can make either point forecasts, or because you make assumptions about the distribution of your distribution, so of your observations. So for example, you can assume that they're drawn from a gamma distribution or a Gaussian distribution or inverse Gaussian distribution or something like that. Then based on your assumptions you make, once you estimate the parameters, you have a full characterization of the distribution you predict for your new observation. So you can use this full distribution assumption to forecast not only make a point forecast, but also forecast the quantiles of your new response for your new observation. Okay, so once again, these, just a quick note, these confidence intervals, sometimes they're not conservative enough because these disregard the uncertainty related to estimates on beta and phi. But however, often in practice, it's still these intervals that are reported, because often in practice, although they're not perfect, they might do well enough for your purposes. Okay, so if the amount of uncertainty on beta and phi is not too large, then these would be reasonable. But otherwise, if the uncertainty on your estimates of these quantities is very large, then these confidence or prediction intervals might not be conservative enough. Okay, so GLMs, they introduce nonlinearity through the introduction of the link function. Okay, so really what introduces nonlinearity within GLM's function is to the function g, which is characterized by expectation of yi given xi. We said it was g inverse of your linear combination of predictors. So really, if G is the identity, we said we fall back on the regular linear model. So it's really by considering a non-identity function G that you introduce nonlinearity within the model. Okay, so you introduce nonlinearity, but in these models, you nevertheless rely on linear combinations of predictors to perform predictions. Okay, so although the linear combination is transformed by the link function, you nevertheless use linear combination of features or predictive variables. And for some applications, that might still be too restrictive. Okay, so sometimes the effect of predictors on the response is not characterized by a linear combination of predictors, but you might have, for example, interaction terms. You might have, or let's say, not. So, for example, if you have something like x1 squared plus x2 squared, then for predictors x1 and x2, then this type of relationship cannot be captured through this exactly. Okay, so for this reason, the GLMs can be too restrictive for some phenomena in practice. Okay, so a quick word, and if you work in actuarial science, in the insurance industry, GLMs are kind of standard methods to predict the severity of insurance claims and the frequency. So severity means when you have a claim, what's the cost of that claim, and frequency is how many times per year you have claims for a given person that is insured. Okay, so GLMs are often used in practice, but for some problems, sometimes its assumption might nevertheless be too restrictive. So it's good to define other types of model which have assumptions that are less stringent. Okay, so sometimes these GLMs can work well enough. They've been used for so long in the insurance industry, so if they didn't work at all, they wouldn't be used as much. But sometimes it's good enough, sometimes it's not, so you need other models. Okay, so again, we'd like to propose models which move away from linearity to represent nonlinear relationships between predictors and the response variable, and the assumption that a linear combination of predictors is used to form predictions up to some transformation G inverse might still be too restrictive. Okay, so if we want to relax this assumption, we can go back to what we proposed in chapter 3, where we can make predictions as linear combinations, not of original predictors in the data, but rather of transformations of the predictors in the data. Okay, so for example, we can come up with a model which makes predictions of the following form. So the prediction for the ith observation is a constant beta 0 plus a linear combination of betas times x tilde ij, where x tilde ij, it's not xij, the original predictor, but x tilde ij is some transformation here of the original predictor. Okay, so it can be, so here I've written a transformation of a single predictor, but it can be a transformation of multiple predictors. Okay, so we can have predictions which are linear combinations, not of original predictors, but rather new predictors based, which are obtained by transforming the original predictors. Okay, so this gave rise to polynomial regression, for example, in earlier chapters, or instead of using polynomial transformations, we could use trigonometric transformations or many other types of transformations. So we'll pursue this idea here of transforming our variables, and we'll study various ways to make these transformations in practice. Okay, but the idea here that we're going to study is to take the original predictors or features and transform them into capital K new features which might be better suited for prediction because they give more flexibility. Okay, so here we're going to see various categories of models or transformations. We're going to study, well, first polynomial regression. So this we've done in the early chapter, but we might repeat a bit on this. And then we'll consider other types of transformations, which include step functions, splines, and finally we'll study a more general type of models, which is called generalized additive models. So the difference here is that for general additive models, instead of providing a transformation to the data, to the model, we'll let the model itself learn the suitable transformation of predictors to be applied. Okay, so this is interesting because you can stay agnostic with respect to what's the proper transformation. You would let the model know it. Finally, at the end of the chapter, we'll discuss also local linear regression, which is some form of combination of linear regression and nearest neighbors method. Okay, so this is a bit of a distinct method, but we'll also introduce this one at the end when we talk about to introduce nonlinear prediction models. Okay, so polynomial regression was already discussed in the previous chapters. This entails taking a predictor, x, and then building new predictors, which are x, x squared, x cubed, x to the power 4, etc., until x to the power capital K for some given integer capital K. Okay, so in that case, you obtain, so x, let's say you have a single original predictor xi, so xi is univariate, then your model becomes yi is the linear combinations of the xij, where j starts at 0. So when j is 0, it's just the intercept beta 0 times 1, up until a monomial of order k plus a noise term. Okay, so this is the polynomial regression model. So as we said, instead of considering polynomials as predictors, you could consider trigonometric transformations. For example, you could have the response being an intercept plus a linear combinations of sines and cosines terms plus a noise term. And here the rationale behind this is these would be, this is meant to approximate the Fourier expansion of a given function. Okay, so many functions can be written as infinite linear combinations of sines and cosine functions. So if we use a finite combination of sines and cosine functions, where of course the constant inside the sines and cosines have to be suitably chosen, so to match the Fourier expansion theory. But if you do that, then you can express the response as a linear combination of these sines and cosines, which would approximate the Fourier expansion of a given function. Okay, so now what happens with that is these types of functions would lead to a periodic prediction function over x until x plus p for any real value of x. Okay, so if you use, so here the denominator in this expression is p. So if you use 2 pi j times your predictor and you divide by p, so then you will have a constant or a like kind of periodic prediction function where the function over x and x plus p constantly repeats itself. Okay, so this is very useful to predict, for example, seasonal phenomena, where, for example, let's give the example of electricity consumption. So in the various seasons, there are patterns of electricity consumptions that tend to repeat themselves over and over in the various years. So, for example, in Quebec in winter, you'll have a lot of electricity consumption. In fall and spring, you might have less. And then in summer, you still might have a lot, but maybe a bit less than in winter because it's so cold in winter that you need a lot of heating, but sometimes summer are a bit cooler, so you don't need as much electricity than in winter. Okay, so you basically have patterns, which is heavy consumption, smaller consumption, heavy consumption, smaller consumption, etc. So electricity consumption can be driven by some periodic type of oscillation, and using these predictors is able to represent such periodic oscillation. Okay, so it's very good for using these predictors is very good for the modeling of seasonal patterns. Okay, so now about the predictors we've just introduced, the polynomial predictors or trigonometric predictors, they have what we call a global structure on the nonlinear function of x. Okay, so what do we mean by a global structure? It means that when we use these features, whenever we change the value of one of the betas, that change impacts predictions for all possible values of the predictor x. Should it be? Sorry about that. But when you change the beta j, for example, it will impact the target regardless of your value of the predictor. This should be xij. Okay, so there's a j missing. This is why I was a bit confused. Okay, so no, it'd be okay. Forget about what I just said. Is because when we use polynomial regression, there's a single predictor, original predictor xi, and the jth predictor x to the power j. Sorry about that. So for polynomial regression, there's a single predictor xi. Of course, I varies from y to n, but each monomial xi to the power j impacts the prediction for any possible value of xi. So let's do an example to illustrate that. So let's say we have, so this is xi, and this is yi hat. Okay, so this is the prediction we make as a function of the value of the predictor in the polynomial regression. So maybe for your estimated set of betas, you have something like, let's say we do quadratic regression, we might have a relationship like this. Now, if you change one of the betas, what happens is you will change your forecast not for a few values of x, but you will change it for all values of x. Okay, so here, if you have something like that, let's go back to blue. So we can see that changing any of the coefficients will change your prediction for all possible values of x. So this is what we mean by global. So each predictor impacts all predictions. Okay, so there's another approach which entails using what we call a local structure for predictors. So what is this local structure? A local structure is when the parameters or the betas in your regression, they impact prediction not for all values of x, but only for a few values of x. Okay, so what are examples of this? Examples are step functions. So let's quickly give one example. So you can have here predictions of the following form. So let's say here, 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 here. So maybe you can have, this is y I hat, this is xi. So if you have a prediction function like this, where this guy is, the height of this is beta 0, the height of this is beta 1, the height of this is beta 2, and the height of this is beta 3. So we can see that if you have a prediction function like this, when you change one of the betas, you could perhaps shift beta 1 and get a new prediction function like this. So here it's the same. Now let's say you shift beta 1 here. Now here would be the same, here would be the same. So you could have other types of predictors where shifting one parameter would impact the prediction for a few values of x, but not all of them. And when you have models like this, this is said to have predictors which have a local structure. Okay, so we can see that having step functions as a predicting function is an example where your predictors have a local structure. Okay, so how do we come up with these types of prediction function? This is what we're going to discuss next. Okay, so how to get step functions as predictions? The idea is to follow the following recipe, which is first you select cut points C1, C2 until CK, which are given constants that you have to select. So these cut points will be referred to as knots. Okay? So now in our example, let's say we have a single predictor xi. In practice, xi can be multivariate and you can still apply this technique. But to illustrate the concept, let's assume that you have one original predictor xi. And then what you can do to transform this original predictor into new predictors, you can define the following new predictors as C0xi is an indicator which is worth 1 if xi is smaller than C1 or 0 otherwise. Then C2 would be a predictor which is worth 1 if xi falls between C1 and C2. C2 would be a predictor which is worth 1 if and only if xi falls between C2 and C3, etc. until CKI, which is worth 1 if and only if xi is greater or equal to k. And for convenience of notation, let's just define C0 being minus infinity and CK plus 1 being infinity. Okay, so this is just to make the notation more convenient in what follows. So in this case, you can have the following linear model where you assume that yi is a linear transformation of your new predictors plus a noise term. And here, your new predictors are the indicator functions. Okay, so basically, if you look at what this function looks like, then you have something like that. Okay, so I'll try to draw it. So this is C1, C2, and C3. So the prediction function like this. So if you take when you take predictions of y, the noise disappears, and the prediction is exactly equal to this term. Okay, so this quantity, whenever xi falls below C1, the only predictor which is worth 1 here is C0, capital C0. And capital C0 is worth 1, so then your prediction here would be equal to beta 0. Then, when x falls between C1 and C2, all such predictors here are, all the indicators are exactly equal to 0, except C1, which is worth 1 when x falls between C1 and C2. So in this case here, the predicted value will be exactly equal to beta 1. And you can continue like this. Here it would be beta 2 until you have ck here, C capital K. So you can continue like this until here it's B capital K. Okay, so you can see that this linear model entails generating a piecewise function for the prediction as in terms of the values of xi. And here, when you do that, if you apply this linear regression model, your linear regression will learn the best values for beta 0, beta 1, beta 2 until beta capital K. Okay, so you see how to get these type of models from linear regressions. And here we can see that the predictors have a local behavior because each of the predictors, they impact a few values for xi, but not all of these values. So for example, you can shift beta 2 and change your predictions for a few values of xi, but not for the other ones. Okay. So now one question is, if you want to have this piecewise prediction function, you must select the knots. So how do you select the knots in practice? Well, this is a very good question. So the idea, if you wanted to do that optimally, you would probably place more knots where the prediction function is expected to exhibit more strong variation, and put less knots in regions where the response is expected to vary less. Okay, so for example, if this is the expectation of y, and this is x, okay, I'll just write given xi, so we're general enough to consider the k-ohms. So here inside the bracket should be xi, okay? So here on this axis is the expectation of the response. This is the predictor. So if you have something like this, where you have one region where this varies abruptly and another region where it's more smooth, then probably the best thing to do is to try to put more knots in this region here, 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 and perhaps less ones here, because having a somewhat constant prediction over these regions is fine, but here you need to have the prediction which varies a lot to match these bumps here. So you need more knots. So if you get something like that, probably your prediction would be here something like this, something like this. Here may be something constant here, and then you'd have a heavy variation. So here you probably have something like this, something like this, and then on this part something like this, something like this, and then probably my 1, 2, 3, 4, and then something like this here. So you need more knots where there's more abrupt variation. So this would be the ideal way to do that, but in practice a lot of people, for simplicity, they use equally spaced knots. So they take Cj being some constant A plus Bj. So basically what a lot of people do in practice would be to have knots equally spaced let's say there, etc. So this makes the selection of knots more simple. It might be less efficient, but uh, a bit more convenient to deal with. Okay, so now once you've selected the knots, getting estimates of beta is very easy because it can be done through linear regression as we've seen in the previous slide. Okay, so we can still express this piecewise linear function within a regular linear model where the predictors are the CJs, which are the indicator functions. So if you use that, then you can obtain a piecewise constant prediction through your linear regression, which is very good. Oh yeah, about knot selection, one thing I mentioned. So the idea to have more knots where it varies the most, it's great, but we said to be convenient, a lot of people place equally spaced knots. But another approach that is very common in practice and which can also be convenient to select the knots is to place knots at the various quantiles of the predictor X distribution. Okay, so for example, if X often takes large value, but often takes very large values, but only seldom takes small values, then it might make more sense to place more frequent knots for larger values of X. So for example, if you have something like that, and if you observe more variables X here, and here you observe few of them, then a lot of people would place a lot of knots here because you have a lot of information to estimate the pattern in this region. And if you have less information to estimate the pattern in this region, then people would use less knots because anyways your estimates would not be very precise. So this is to determine the location of knots, but another issue is how many knots should I use? Well, the answer to this is this can be determined through cross-validation. So for example, you can try a model with 100 knots, with 10 knots, with 1,000 knots, with 4 knots, whatever. So for all these values, you can assess how well your model does through out-of-sample performance assessment, and if you would basically select the number of knots which would give you the best performance out of sample. Okay, so this is the approach you can pursue to determine the number of knots. Okay, so now we've seen how to obtain piecewise constant prediction functions, but there are issues with constant piecewise functions. Okay, so first there are constant piecewise patterns. A lot of patterns are not constant piecewise, but rather vary smoothly. And so, for example, you have your function. Not only is it constant between the knots, but on the knots there are sudden discontinuities in predictions. And if your pattern varies smoothly, it's not a good idea to have discontinuities. So we'll see how to obtain better local predictors to still have a local prediction model, but instead to have more smooth predictions. But this will be discussed next time in the next lecture. All right, so thank you, and I'll see you for the next video.